How to avoid a vortex ring state in helicopter operations. A vortex ring state may occur in various helicopter operations. More than 95% of vortex ring state accidents or incidents are pilot-induced. That means that the pilot brings the helicopter in a flight phase where a vortex ring state can build up. Low-speed operations outside of ground effect are particularly critical to build up a VRS. For example, external load operations, power line inspections, operations with reduced visual references due to sun and shadows, during the night, when the light is blinding, operations at the performance limit due to collapsing updrafts, mountain approaches, special operations, rescue hoist operations. To prevent a vortex ring state, we need to know more. Abbreviations and units used in these videos. Warning: all graphics presented in this video are for illustration only and must not be used in the helicopter. The exact values must be taken from publications of the corresponding original equipment manufacturer datas. The Vuichard recovery technique and other special techniques shown in this video requires specific training with qualified flight instructors, both in the helicopter as well as in the flight simulation training device, to prevent dangerous situations and negative training. This video allows the vortex ring state to develop further for demonstration. When practicing, recovery should be initiated at the first sign, lightness in the seat, in the incipient stage of the vortex ring. Rotor disc load categories. In this movie, we use the R22 as a representative of the low disc load category, the H125 as a representative of the medium disc load category, the AW139 as a representative of the high disc load category. Different rotor disc load categories. Low disc load under 20 kilograms per square meter or under 4 pounds per square foot. Medium disc load between 20 and 30 kilograms per square meter or between 4 and 6 pounds per square foot. High disc load between 30 and 50 kilograms per square meter or between 6 and 10 pounds per square foot. This film does not specifically address the category of very high disc loads, such as the AW609 or V-22 tilt rotor aircraft, which exceed more than 50 kilograms per square meter or 10 pounds per square foot. Calculation of the induced velocity in function of the rotor disc load and the air density. The formula to calculate the induced velocity. VI equals induced velocity in meters per second or in feet per second. Fn equals weight force in Newton or pound force. Rho equals air density in kilograms per cubic meter or pound per cubic foot. S equals rotor surface area in square meters or square feet. Calculation of the induced rotor velocity. We show as an example the H125. This results in an average induced velocity of 10 meters per second, or 32.8 feet per second. how the vortex ring state builds up. The 3 prerequisites to build up a vortex ring state. Entering from above in the VRS sector. First, an induced airflow, or downwash, almost perpendicular to the rotor disc on both axes, X and Y. Here, you see the visualization of induced airflow in hover out of ground effect. Second, an exactly opposite ascending airflow, VZ. The ascending airflow, VZ, at least half of VI, is either generated by the movement of the rotor in the same direction as the induced rotor flow, or by an updraft against the induced rotor flow. A combination of both is also possible. Third, sufficient power at the rotor at a torque of about equal or greater than 40%. Rules of thumb. The minimum torque to build up a VRS. Read the torque value on ground at nominal rotor RPM and add 15% of torque. Remember, the 3 prerequisites to build up a vortex ring state are: first, second, third. If one of these 3 prerequisites is not met, the VRS cannot build up. X and Y axis of the rotor disc. First, an induced airflow perpendicular to the rotor disc on both axes. Second, an exactly opposite airflow, VZ, with at least half of the induced airflow. Third, a torque about equal or greater than 40%. Visualization of the buildup of a vortex ring state. The induced flow must cross the rotor disc area at 90 degrees. There is no induced flow at the center of the rotor disc, and the induced flow is greatest at the blade tips. An exactly opposing airflow, VZ, develops because the helicopter is descending or due to an updraft. At some distance below the rotor, where the updraft meets the induced airflow, the induced flow is deflected outwards and upwards around the rotor blade tips. If the conditions are right, then the induced flow is sucked back down through the rotor to form a closed circuit. Now, the vortex ring state has been established, and the helicopter is trapped. Due to the constant reacceleration of the induced airflow, the thrust decreases and fluctuates. The vorticity in the ring induces a downwards velocity component. These downward induced velocities cause the ring to propagate downwards. More power on the rotor makes the vorticity in the ring stronger and increases these induced velocities, making the vortex descend faster. Some of the air flowing through the center is also sucked in by the rotor, forming a very small vortex ring that turns in the opposite direction. This small vortex ring has little effect on the descent of the helicopter. Due to the low orbital blade speed in the center part of the disc and the high sink rate, a blade stall can occur. Pulling on the collective only increases the stall area. It is astonishing that, if you could remove the helicopter by a magic trick, initially, the vortex ring would continue to sink with the same speed until it dissipates. Rules of thumb for the vortex ring state, key data calculations. Rate of descent. Without an opposing VZ thermal or dynamic airflow. Rules of thumb to calculate the minimum ROD required to build up a vortex ring state. Entering from above in the VRS sector, true airspeed equals 0. Rate of descent equals induced velocity divided by 2. Example at sea level, maximum takeoff weight for the R-22. The minimum rate of descent required for VRS is 3.7 meters per second, or 720 feet per minute. For the AW139, the minimum rate of descent is 6.7 meters per second, or 1,300 feet per minute. The range is between 500 and 2,000 feet per minute, or 2.5 and 10 meters per second. The range is between 800 and 3,000 feet per minute, or 4 and 15 meters per second. The range is between 1,200 and 4,000 feet per minute, or 6 and 20 meters per second. Rules of thumb to calculate the final rate of descent in a vortex ring state. Rate of descent equals induced velocity multiplied by 2.5. Example at sea level, maximum takeoff mass. For the R-22, the final rate of descent in the VRS is 18 meters per second, or 3,600 feet per minute. For the AW139, the final rate of descent is 33.7 meters per second, or 6,600 feet per minute. Final rate of descent range in a VRS for a low disk load. Now, you see an R66 with a low disk load in front of a cliff in a full vortex ring state with an impressive rate of descent. For a medium disk load, you can now see an AS350 in front of an Eiger north face, which transitions into the vortex ring state. Note the impressive sink rate by taking a reference point in the wall. For a high disk load, the final rate of descent is impressive. It's greater than 6,000 feet per minute, or 30 meters per second. Final rate of descent in numbers of floors per second in a vortex ring state at mean sea level. For a low disk load, 6 floors. For a medium disk load, 8 floors. For a high disk load, 11 floors. This corresponds to 65 kilometers per hour for a low, 86 kilometers per hour for a medium, and 119 kilometers per hour for a high disk load. Be aware that, without applying a vortex recovery technique, you will hit the planet at these speeds. With increasing altitude, the air density decreases. To generate the same thrust, a higher induced velocity is required. Final rate of descent at the density altitude of 5,000 feet. The rate of descent in floors per second increases to 7 floors per second for a low, 9 floors per second for a medium, and 12 floors per second for a high disk load. Now at the density altitude of 13,000 feet, the final rate of descent rises to 10 floors for a medium and to 14 floors per second for a high disk load. This corresponds to 108 kilometers and to 151 kilometers per hour. Due to the tremendous sink rates in the vortex ring state, it is essential to reflexively apply a recovery technique because every second lost results in an enormous loss of altitude. For a low disk load, we will demonstrate the range required to enter in a vortex ring state and the range for the final rate of descent. If you start a vertical descent from hover into the range required to establish a vortex ring state, the vortex will build up and the vertical speed increases to the final range. If you start from a vertical power-off descent and add power by slowly increasing collective, the rate of descent will decrease and you will enter in the vortex ring state and vertical speed increases to the final range. You can see what happens for the medium disk load with the range required to enter in a vortex ring state and the range for the final rate of descent. You can see what happens for a high disk load with the range required to enter in a vortex ring state and the range for the final rate of descent. How does the weight influence the different vortex ring state parameters? This table shows how the rate of descent changes in the low disk load categories based on the rules of thumb calculations, both for the initial and the final rate of descent in the VRS at maximum takeoff weight. and at 75% of this weight. 75% usually corresponds to the pilot alone on board with fuel for about an hour. At maximum takeoff weight, the rate required to enter a VRS varies from 720 feet per minute for the R-22 to 820 feet per minute for the Cabri G2. The final rate of descent in VRS varies from 3,600 feet per minute for the R-22 to 4,100 feet per minute for the Cabri G2. At 75% of maximum takeoff weight, the rate required to enter a VRS varies from 620 for the R-22 to 700 feet per minute for the Cabri G2. An average reduction in the rate of descent of 100 feet per minute in the final rate of descent varies from 3,130 feet per minute for the R-22 to 3,630 feet per minute for the Cabri G2. An average reduction in rate of descent of 500 feet per minute. This table shows how the rate of descent changes in the medium disk load category based on the rules of thumb calculations. Now, you can compare how the values of the different medium disk types change. Note, at 75% of maximum takeoff weight, the H125, for example, will behave like a helicopter with low disk loading. This table shows how the rate of descent changes in the high disk load categories based on the rules of thumb calculations. Now you can compare how the values of different high disk types change. This table shows how the rate of descent changes for the very high disk load, a W609 tilt rotor, based on the rules of thumb calculations. Now you can compare how the values of the AW609 change depending on the weight. In which low speed range can a vortex ring state occur? The true airspeed range to build up a vortex ring state in function of the rotor disk load. The true airspeed range is omnidirectional for a low disk load between 0 and 10 knots, or VI multiplied by 0.8. For a medium disk load between 0 and 20 knots, or VI multiplied by 0.8. For a high disk load between 0 and 30 knots, or VI multiplied by 0.8. The relation between true airspeed and indicated airspeed and WOOLOMETER during hover, outground effect, and low-speed operations. The trim string, which I call the WOOLOMETER, is a very important instrument to avoid VRS. It hangs straight during hover and low-speed operations until the true airspeed deflects the induced flow or downwash. The WOOLOMETER is also capable of displaying the true airspeed, not only from the front, but also from the side. Slowly, the true airspeed increases and the WOOLOMETER starts to move. Once the WOOLOMETER rises stably, you're protected from a VRS because the true airspeed could deflect the induced flow so that it no longer crosses the rotor disk area at a 90-degree angle. Thus, the first condition to build up a VRS is no longer fulfilled. Here, you see how the WOOLOMETER simulated in the R-22 simulation of loft dynamics with 14 knots from the right. The WOOLOMETER points stably upwards. Again, you are protected from a VRS. Therefore, I recommend all helicopter manufacturers to equip their aircraft with a WOOLOMETER. Here, you see the induced flow of the 3 rotor disk load categories. At a true airspeed of 0, the induced flow crosses the rotor disk area at 90 degrees, and the WOOLOMETER in the indicated airspeed shows 0. If we add 10 knots of headwind, we see that the induced flow is deflected only in the category with low disk load, R-22. The WOOLOMETER points up, and the indicated airspeed is 10 knots. Now, we increase the headwind to 20 knots. The larger headwind is sufficient to deflect the induced airflow, even in the medium disk load category, H125. The WOOLOMETER also points upwards in the medium category, and the indicated airspeed is 20 knots. If the headwind is increased to 30 knots, it's sufficient to deflect the induced airflow, even in the high disk load category. If the AW139 were equipped, the WOOLOMETER would also point upward. In summary, for a high disk load due to the high induced airflow up to 30 knots omnidirectionally, are required to deflect the airflow and avoid a VRS. Different vortex ring state buildup sectors in function of disk load. VRS buildup sector for helicopters with low disk load. At 0 knots TAS, the lowest point of the danger sector usually corresponds to a power setting greater than 15 inches of manifold pressure or around 40% torque. The lowest point corresponds roughly to the induced velocity, VI, multiplied by 1.5. Within the shaded area, the VRS can build up. First of all, it's imperative to avoid this area during an approach and during low-speed operations by keeping the rate of descent below 300 feet per minute at an airspeed below 30 knots. From an operational standpoint, there are 3 ways to enter this dangerous zone. From the side, by reducing speed at a constant rate of descent greater than 500 feet per minute. Once the true airspeed is more or less stable inside the dangerous area, the VRS builds up and the helicopter literally falls from the sky. From above, by increasing rate of descent into the dangerous area. This could mean, for example, that you cannot maintain hover out of ground effect due to lack of power, that the VRS buildup and the helicopter will fall out of the sky. From below, by decreasing the rate of descent from a very low power approach or low speed auto rotation. As soon as the true airspeed is more or less stable inside the dangerous area, the VRS builds up and the helicopter falls out of the sky. Now, the 3 entries for medium disk loads. From above, from the side, from below. This can also occur during sling operations. Now, the 3 examples of entry for heavy disk loads. From below to hover in headwind. From above to hover in tailwind. From below to hover in tailwind. VRS sector in function of true airspeed. Now, we analyze the sectors for a medium disk load at plus-minus 10 knots true airspeed. The dangerous rate of descent is approximately between 1,000 and 2,300 feet per minute. At 20 knots, the rate of descent is between 800 and 1,200 feet per minute. Note that the dangerous range can increase up to 3,000 feet per minute if you reduce speed on the approach to hover. Therefore, in the low speed range, it is crucial to keep the sink rate below 500 feet per minute. Risk of leveling off from the nose up or nose down attitude near or within the VRS buildup sector. Please note that any leveling off from the nose up or nose down attitude can bring the induced flow to the 90-degree angle to the rotor disc. Thus, the first condition for the formation of a vortex ring state could be fulfilled. As long as the leveling occurs outside the danger area, the vortex ring state does not build up. If the leveling occurs within the danger zone with sufficient power, the vortex ring state builds up and the helicopter literally falls from the sky. Difference between blade tip vortices, main rotor vortex, and vortex ring state. In hoverflight, the blade tip vortices descend helically and therefore do not come into contact with the following rotor blades, nor during the acceleration phase. However, as soon as you start to descend from the hover, the blades will hit the vortices of the preceding blades. This creates a vibration that can be felt and heard in the helicopter. The frequency of these vibrations depends on the number of blades and the angular velocity omega. As soon as the H125 goes from hovering to a slight descent, you can very well hear a rattling sound when the vortices are hit by the following blades. In the helicopter, you can feel the vibrations generated by the rotor blades. However, as soon as the rate of descent is reduced, the vibrations and rattling instantly disappear. As long as the helicopter is at zero airspeed, the induced flow is vertical below the helicopter. As soon as the helicopter changes to a slight forward flight, main rotor vortices are formed. Here, you can see a hover outside the ground effect with a headwind of about 20 knots. In the next sequence, we see the influence of this main rotor vortices on the helicopter during the approach. Let's take a look at the impressive wake of the main rotor vortices. As long as we're flying at speeds above 30 knots true airspeed, the main rotor vortices has no effect on the helicopter, even in descent. It can be extremely dangerous if a lighter aircraft follows or crosses this wake. Helicopter pilots must fly in such a way that they never fly ahead or cross the expected flight path of light aircraft or paragliders. This massive wake slowly descends behind us. If we could see this massive main rotor vortices in the rearview mirror, we would fly very differently. We now start an approach. We descend and suddenly find ourselves in the middle of the main rotor vortices. The wolf is now behind us and ready to swallow us. When we now reduce the speed further, the vortices is sucked in by the rotor, initially in the rear part. If we do not recognize it and reduce the speed further, the helicopter is suddenly in the dynamic induced vortex ring state. If the pilot realizes this, he can prevent the vortex ring state. As long as you don't feel a low G, the situation can be saved by additional power with the collective, by increasing the speed with the cyclic or both. The fully developed Vortex Ring State on the SA-3-15 Llama, the only footage ever made that properly visualizes the vortex ring state of a helicopter. Detection of a fully developed vortex ring state. The 4 signs of a vortex ring state are: Number 1. A sudden low G, 0.2 to 0.8. That is the feeling of lightness in the seat. The intensity of the low G, 0.2 to 0.8, depends on the rotor disk load, the air density, the rate of descent, and the power on the rotor when the VRS is built up. It takes on average 2 to 5 seconds of low G to reach the final rate of descent in VRS. Once the 3 conditions are met, the vortex ring state builds up, and you feel a low G for 2 to 5 seconds. The intensity of the low G depends on the disk load, the power on the rotor, and the density altitude. A clear sign of a low G is the feeling of lightness in the seat. As long as you perceive the low G, the helicopter continuously increases its rate of descent until the final rate is reached. Here is the sequence of an H125. At the moment of entry in the VRS, the G meter goes from 1 to 0.76 G. Then, a Vuichard recovery is immediately initiated, and the helicopter abruptly stops its descent. The G meter then reads 1.5 G, and the recovery is complete. Number 2. No response when increasing power by pulling the collective. It feels like the collective is disconnected. Number 3. A sudden and significant reduction in the vibration level of the main rotor. The specific vertical rotor oscillations with a frequency of 2, 3, 4, 5, 6, omega, depending on the number of rotor blades, suddenly disappear because the induced flow now circulates in a closed physical circuit, and the rotor blades consequently run in less turbulent air. Number 4. During the VRS, a low frequency of random buffeting is perceptible each time the vortex ring loses air. Without using the Vuichard recovery technique, the G meter would read about 0.5 G until the final descent rate of about 5,000 feet per minute is reached, and then it would read 1 G again. Vortex ring state detection and alerting systems in modern helicopters. Modern helicopters are increasingly equipped with so-called vortex prediction systems that warn the crew, based on current airspeed and rate of descent, that the helicopter may enter the VRS danger area. First, the yellow caution light comes on, prompting the crew to check the power. Here, the situation can still be corrected by increasing the power with the collective, or by increasing the speed with the cyclic, or both. At the second warning level, the red warning light, the helicopter is in the imminent vortex zone. But as soon as you feel a low G, immediately apply a Vuichard recovery. This is the best way to quickly escape a vortex ring state. Although such warning systems are helpful in preventing VRS, even these systems have their limitations. In part 3 of this series, we'll show in more detail where special caution is required despite such warning systems. What you're now going to learn in part 2 of 3 is how to avoid a vortex ring state during normal approaches with emphasis on the safety window check, correct use of the WOOLOMETER, steep approaches, approaches with a constant deceleration, approaches with a rapid deceleration, approaches with an insufficient or a constant power setting, dynamic approaches, quick stops, hover out ground effect, operations with limited power, final approaches with poor or loss of visual references, night operations, operations in updrafts, operations in collapsing updrafts, operations in downdrafts, wind shears at low speed, or HOGE operations, multi-engine operations, one engine in operative training, Category A operations and training, tailwind operations, go-arounds in different wind conditions. Many thanks for the great support goes to the following Swiss companies: Aerial Stage, your premium aerial footage; Air Glaciers; BSV Production, your premium film production company; Centurium Aviation; Heli-Lint; Valair; Leocopter; and Loft Dynamics, professional virtual reality helicopter training solutions.
Thank you very much for a donation to the RAS.org. Without your financial help, it will not be possible to produce further safety videos to make the global world of helicopters safer.